heard particularly in the first talk a lot about diagnostics for error covariances, and I'm now coming back to the background error covariances, how to estimate part of it directly from observations and how to use that for localization. It's based on the cross-validation tool, which Krishna has shown us some very nice results with. And yeah, this cross-validation tool, Krishna used it to verify the impact of observations or to find observations which were problematic. But in principle, the skill of this tool is that it compares an equation which compares two quantities, which are the two ops minus first guess departures and background error covariance from the ensemble taken from the ensemble and localized with a localization function. And so the equation here, we've seen that before, is just a special case of the covariance, that the covariance of ops minus first guess is background part plus observation part. And when I take a non-diagonal element here between observations which are not correlated and get my consistency relation. So I get an estimator that already was used before, that you get a true estimator, if under ideal conditions at least, for the background error covariance matrix. And that's what the diagnostic cross-validation tool is based on, which, however, has been derived from the FSOI verification function, which tests how the analysis fits better to the verifying observations than the background. So here at verification data, I take observations, and when you simulate another observation, then this can either pull the model towards the verifying observations or away. And the traditional established FSOI formalism asks the question whether this improves the fit to the verification data. When I do cross-validation, I ask a very similar question, but yeah, it's simpler, which I believe is a big strength of this, to be simple, a little more simple. I just ask whether the model is pulled in the right direction. And how it was developed, the FSOI standard method decomposes the cost function into contributions related to the individual observations. And I have taken these contributions and further decomposed them in two parts, where one of the part is my cross-validation diagnostic, which exactly tells us whether the model is pulled in the right direction, and it's proportional to the product of the two ops minus first guess departures and the model and an ensemble covariance matrix. And yeah, this has to be, the way it's defined, it has to be, with the minus sign, has to be larger than 0 to be beneficial. And in the diagnostic tool, what Krishna has shown you very nice examples of, this is compared also to a reference curve, which Krishna mentioned, the green curve, which when you compare the two, you actually check on the consistency relation I mentioned. So comparing the blue and the green curve, what Krishna did, you compare this relation. So, and now I want to use this relation to look at the localization of the B matrix. How do you do that? For that, I go back to the verification or cost function and realize that it's a function actually of the localization function, the localization factor, so I can differentiate it with respect to the localization factor. And this, if I'm at the minimum, this has to be 0. So doing all this, I find that the optimal localization would be proportional to the ratio of my two cross-validation diagnostics, but of course with no localization, with the localization, because I don't want the localization function on this side of the equation. I want to compute it, the optimal value for it. So before I show you some results with real observations, I wanted to quickly come back to the assumptions, what I see as the most problematic assumptions which go into this thing. And the most problematic assumption is actually our consistency relation. The JB here is proportional to the product, and this consistency relationship is easily derived by composing optimized for states as a difference between observation error and background error. We've seen that before, and in observation space, of course, if you do that for both observations, you get 4 terms here. And the first of these terms is actually the average of this is our background error covariance. And so the assumption is that the other components all vanish. And as I mentioned, the observation error has to be uncorrelated, it has to be unbiased, and the same is true between of model and observations. They have to be uncorrelated and unbiased. So that's I think, in principle, not the worst thing we're dealing with in data simulation, but for this diagnostic, it's, I think, can be quite sensitive here. So I show you some results with real data for here the vertical correlation for solar wind. You get from radio zone data and from aircraft data. On the x-axis here, this is in logarithmic pressure coordinates, the distance between the vertical distance between the 2 observations. Sorry, and because I'm interested in here only in vertical localization, I've restricted horizontal distances to 40 kilometers, and also the observations have to be plus minus 20 minutes from the analysis time. And sorry, I've shown you here the big differences between, sorry, there's a misprint here. This has to be logarithmic P2 over P1, of course. I've forgotten to correct this. Yeah, the big differences here are the tails. That's why I show you logarithmic plot, and also I'm showing you a Gauss function, or Gaspari cone if you want, if you're more used to that. Here with the localization length of 0.2 in these low pressure coordinates, which fits reasonably well, but of course the tails are not Gaussian, they're exponential, so something like the Huber norm fits much better. But the scale is the right one, I think. And I compare this with work. There has been a lot of work which computes the optimal localization under the assumption that the only thing you have to correct is the sampling error with respect to small ensemble size. There's been a lot of theoretical work on it, and also some quite nice practical work by Tobias Necker, where he did work with the 1,000-member ensembles and said if you have only 40 members, what would be the optimal way to localize them, given that at 1,000 members it has converged more or less. So he gives different, the curve for solar wind is the red curve here, and he did it for different heights, gave the localization function. But what we see, it's much, the scale is much broader here than for what I get from observations. For comparison, I put you here the Gauss function with localization length 0.2, and we see really there's a huge mismatch in this localization scale between this 1,000-member ensemble and what we get from observations. But there are also some similarities with what Tobias did in what I found from observations. For example, he is right, you get different answers for different heights, and he also found that the localization length scale increases with height, the optimal one. That I also found that. Also, one point here I would like to draw your attention are these spikes here, these single bins. in the blue and the green curve on the tails, which I first thought were just noise, but they actually occur in both independent data sets. And it turns out this is actually the signal from the surface, and that's something which Tobias also found in his data, that there's a signal from the surface which you probably should not damp if you can.
You have 3 minutes left.
Yeah. Okay, I will have more data to show. Just to show you how things vary for different systems here for our limited area model. I get a little smaller localization length scales, and I get different at different times, January and June. I also get slightly different answers. So it varies in space and in times. What I get as answers. The interesting one was looking at temperature in our global model. I first was a little shocked because the radio sound temperature disagreed quite strongly in this close range, which I thought where I thought the close range here for solar and wind, that's where the two observing systems agreed. But then I found some radio zones which had a very strong bias, 0.5 degree, and when I excluded them, I got this blue line, which is an extremely nice correspondence, actually. I also did some work for horizontal scales, but I think I better come to the conclusions. So can we estimate the localization length scale? So the answer is a clear in principle yes, but we need very high accuracy observations because everything is very sensitive to systematic errors or misspecifications of the observations and the model, and also scale mismatches. I believe what you have at small distances here, the disagreement, which is quite now occurs all the time, is mainly the scale mismatch, while the tails are more quite sensitive to systematic errors. Generally, you have a sampling issue because you get different answers from different heights and different times, and observations, they are not distributed homogeneously at all. And if you want to resolve different times or different regions in space, then you have problems with noise if you want to resolve it too nicely. But still, I would say that testing covariances with observations, which are our access to reality, I see it as a very important constraint. And I think, we get some, I think the length scaling we're using in practice is actually the right one. That was, I would say, one answer I got so far from this work. Thank you very much.
Thank you very much, Olaf. There is a question already by Tobias Necker, who's asking, could your method also be used to learn something about inflation?
Yeah, I think it's a difficult one because the spread, as you see here at small distances, they all disagree quite badly. Here, one would be if there was no inflation needed. But I think I believe the scale issue that you have point observations and they are not representative for the whole grid box. So when observations are far away in the grid box or close to each other in the grid box, you expect if there are variations across the grid box, expect disagree that they vary there. And when you take the observations which are very close to each other, then you get this strong by factor 2 overestimation here compared to the aircraft data, which are probably usually further away from each other. So that's my explanation of the difference between aircraft and radiosondes here. It's very small distances. So then I think you need to address that problem if you want to learn something about the spread of the system.
Thanks a lot. There's one more question by Daisuke Hotta. Sorry, I think it's, yeah, there's more questions. So I would kindly ask you to answer those on the YouPad in interest of time. So thanks again.